For this year's Governor's STEM competition from McDowell, Daniel Harmon, Matthew Lee, Siyoung Kim, and me, Sachin Ashok, worked together to create a prototype that could actually save lives in our community and throughout Pennsylvania.
When considering the fundamental ideas around which we are going to design and create our product, the first that came to mind was finding a problem we saw within our community that we believed we could solve. We cycled through various project ideas, from things like making snowed over roads safer for drivers trying to clean up the local Lake Erie. But what we inevitably settled on was worker safety on the job. Each year, tens of thousands of American workers suffer head injuries while on their work sites, and the Bureau of Labor Statistics tells us that in 84% of those cases, the workers are not wearing their hard hats whatsoever. Our team saw this lack of safety as a problem that could be solved with our engineering design. Hard hats are required by federal OHSA regulations on job sites where the objects hanging over people's heads, and companies that don't enforce the policy within their workforce get fined if they're caught. So to help companies by preventing severe worker head injuries and guaranteeing that they won't get fined for lack of headgear, we create a system to detect when workers take their hard hats and relay the information to the site manager.
Whenever you put an idea into a physical form, it is of the utmost importance that we consider the engineering design process to outline and organize our thoughts. At first, we were a little bit stumped on finding a problem to solve. By using our community business connections, which we will go further in depth on down the line, we were able to identify a clear need in our community for increased occupational safety. We dived into research, noticing that many workplace accidents could just be prevented by the usage of a helmet. Working with OSHA employees, we actually thought that the best way to solve that system was to implement a system in which OSHA inspectors and supervisors can tell if an employee was wearing a helmet or not. The hardest part was deciding how we would implement this idea. After meticulous planning and weighing of our options, we came up with two possible solutions. One, that we place a temperature sensor in the helmet to notice the presence of a human, and the other that we will place a force sensor in the helmet. We decided on the force sensor as the temperature sensor seemed extraneous. Since we didn't have the budget to buy a more expensive infrared sensor, buying a lower cost temperature sensor with a greater margin of error could lead to more bugs and misidentification while still being more expensive than the force sensor. Furthermore, we only truly needed a linear Boolean output to determine whether the worker was wearing the hat or not. We didn't really need that level of precision that the temperature sensor had to offer. Finally, having chosen our parts, we got to work. To create the prototype itself, we bought 2 Arduinos, resistors, a force sensing resistor, and a transceiver. We soldered everything together, formulated the code, and ended up with a prototype. We tested the prototype on my head, and boom, we were finally getting a linear output concurrent with the actions that we were actually performing. Noticing that readings were coming too often, we configured the prototype to only output every few minutes in order to not bother the supervisor or inspector.
For the STEM competition, we mainly interacted with Mr. Ashok at WebTech and Mark Harmon at OSHA, helping us identify a need in the community, providing us with resources for our research, and vetting our proposed solutions. Through the various connections that we cultivated, we were truly able to improve our project so that we could maximize the amount of people we could help with our idea.
To begin the engineering process, we first needed an idea. Settling on something meaningful and concrete was one of the most difficult portions of this whole process. So we got to a point where we decided to source our ideas from the community connections we had around us. In doing so, we came up with the idea of creating a system to recognize when workers were or were not wearing their hard hats while on a job site. With this goal established, we began running through different potential designs to make what we wanted. We considered temperature sensors and force sensors, but ultimately decided that the force sensors would be more effective at a lower cost. Once we had decided on the force sensors, it all came down to designing and prototyping different designs. The basic requirements that we needed out of our system was a sensor within the helmet that could relay its readings back to a computer remotely. To achieve this, we soldered a battery holster, a force sensor, and a transmitter into an Arduino Nano and placed that inside of the helmet. On the other end, we wired the receiver to a second Arduino and attached that to a computer. With this design, we were able to achieve our ultimate goal of creating a device that ensures workers keep their helmets on by alerting their managers if they take them off.
This product truly has the ability to save thousands of lives from traumatic brain injuries. In order to get this product out to as many people as possible, we would have to mass produce these devices. To calculate the cost of mass production, we need to find the cost of our direct materials, the cost of direct labor, and the cost of our manufacturing overhead. For the direct materials, we need to include the cost of 2 Arduino Nanos, 1 battery clip, 1 battery, 1 force-resisting sensor, 1 transmitter, 6 stripped wires, and 1 receiver. This comes out to $40.73. Furthermore, to find the cost of direct labor, we need to multiply the direct hourly wage by the time it takes to complete 1 unit of the prototype. It takes 15 minutes to make 1 unit, and the direct hourly wage is $16 an hour for the 50th percentile of labor, so it comes out to a direct labor cost of $4 per unit. Finally, to calculate the cost of manufacturing overhead, we need to consider the cost of utilities, indirect materials like solder or soldering iron, physical costs, and financial costs. Accounting for all of these, the total cost of manufacturing overhead comes down to $10.68 per unit. With all of these elements, the cost of mass production comes down to $55.41. This is definitely a more liberal estimate, as it doesn't include manufacturing rebates and lower costs when more units are ordered.
When I don't have the helmet on, the force sensor reads 0, and then I put the helmet on, and as we can see, the force sensor no longer reads 0. Take the helmet back off, force sensor reads 0.